Good morning. All right, this morning I have the pleasure of introducing Dr. Ranthony A.C. Edmonds. I am standing in Dr. Walker's place. She sends her regards. She is not feeling well. Dr. Ranthony A.C. Edmonds is a National Science Foundation postdoctoral researcher of mathematics affiliated with Duke University and a SciAm MGB Early Career Fellow. She earned her PhD in math in 2018 from the University of Iowa and her master's degree in mathematical sciences from Eastern Kentucky University in 2013. She has a bachelor's degree in English and mathematics from the University of Kentucky, which she earned in 2011. Her research interests include applied algebraic topology, data science, commutative ring theory, mathematics education, and she is deeply invested in quantitative justice, that is, using mathematical tools to address societal issues rooted in inequity. Her current work in quantitative justice involves applications of mathematics and statistics to electoral redistricting. This semester, Dr. Edmonds is a Berlekamp postdoctoral fellow at SL Math for the semester program on algorithms, fairness, and equity. She has accepted a tenure-track position at Ohio State University as an assistant professor in the Department of Mathematics to begin in 2026 upon the completion of her postdoctoral studies. Without further ado, I welcome Dr. Ranthony A.C. Edmonds.
Okay, I think we're good. Okay, so bear with me. We'll figure out. There may be a hiccup with the mic at some point during the talk. But good morning. Good morning. I'm really excited to be here. This is my first AWM Research Symposium. It won't be the last. And I thank you so much, Dr. Jones, for introducing me, and thank you so much, AWM, for the invitation, and for you all for being here. If you are on Pacific time like I am, it is very early right now, but I just really appreciate you being here. I think we're going to have a good time. So, as was mentioned, I am really interested in this idea of quantitative justice, which is, okay, let's see. I don't want to be beholden to the podium, but I think if I am messing with the mic, it'll be distracting. I'll just stand for a minute, and then I'll walk when I feel like I need to walk or something. Okay, so I'm interested in this idea of quantitative justice, right? This idea of using mathematical, statistical, computational tools to address problems that are rooted in some sort of social inequity. And one thing I wanted to start with is sort of just some pillars of quantitative justice, namely, how do you know that quantitative justice work is happening, right? And so it is necessarily interdisciplinary. Social scientists have been using quantitative tools for decades and decades, so we are late to the party as mathematicians thinking about social justice in this particular, from this particular perspective. But in particular, I just wanted to share that quantitative justice is a sort of new and emerging research field, and what I want to do today is talk about a particular domain that falls under the umbrella of that field, which is electoral redistricting, and what fairness looks like and how mathematical tools can help support community efforts in that regard. So I'm going to sort of come back to this framework throughout the talk, but if you're an applied mathematician, this sort of pipeline should feel familiar. You have a particular problem from some sort of interdisciplinary domain, and you need to quantify it. You need to determine what sort of models or tools you're going to use to help solve your problem, and after your analysis, you have some sort of output. One thing that I really wanted to highlight is that when we're thinking about quantitative justice, our output is not just research products or papers or conference talks. Our output is really focused on how do we support our community partner, right, in the efforts that we're assisting them with. How do the analyses that we do directly contribute to solutions and inform the social problem at hand? So today, I want to start with this really big question and kind of narrow it down. So how do we secure political representation for marginalized communities in the United States? Like, this is the underlying question, the motivating question behind this research that I'm going to present today. But this is a really big question. Like, I don't know. There are a lot of people who have tried different approaches. And so the perspective that I want to think about is, what about in redistricting, right? In this particular way of securing representation, of thinking about our electoral system, how do we secure representation for marginalized communities by thinking about what are called communities of interest in this redistricting process? So if you're unfamiliar, I want to take a few slides just to sort of explain what redistricting is. I did not know what this was, I don't know, a year and a half ago. So I just want to kind of be thorough. Forgive me if this is familiar already. Actually, it's okay if you already know, because then you'll just know some more. Okay, so redistricting. So in the United States, every 10 years, the government does a census, and they collect population data. So once we understand how many people are living in a particular state, the government apportions seats to that state based on that population. So they are apportioned a number of representatives. So for instance, in Ohio, in the last redistricting cycle, we were apportioned 15 congressional districts. What this means is that a redistricting will happen after the census, where they take the state's geography and partition it into pieces. So Ohio was split into 15 pieces, and within each piece, which is called a district, there's elections that allow you to elect representatives. And so we can hold 15 elections that will elect 15 Congress people from Ohio to Congress. And so the reason that redistricting is really important, and the reason we think about fairness and maps so much in mathematics, is that given a distribution of votes, the choice of map dramatically affects the outcome of an election, right? So let's suppose you have two parties, red and blue, with a slight majority for the red. The choice of map that you choose, the way that you choose to partition the state's geography, dramatically affects the representation and how you interpret the votes that you receive. Okay, and so here are some examples from North Carolina. These are 3 actual maps. The first one is from 2012, the second one is from 2016. And as you can see, the maps may look similar, but their outcome, right, the number of representatives that you get, given a particular voting pattern, changes. So in the first 2 maps, even though they're slightly different, you still have the same number of red representatives to blue representatives. And the last map, you have much more reciprocity. Okay, so is everyone following redistricting? We partition the state into pieces, the maps really matter. Okay. Okay, so when things get kind of hairy, a little nefarious, is when you manipulate these boundaries on purpose, right? If a particular party draws districting lines to maximize their representation. And this process is called gerrymandering. It's named after a famous political cartoon from Boston Governor Gary, who was trying to draw a salamander-shaped district to sort of support, I think, the Democratic Federalist. This was quite some time ago. I'm not as brushed up on my 1812 politics, but this is sort of the origin of the term. And so when we think of gerrymandering, we think of manipulation, right? The opposite of fair. And so when we're thinking about fairness, a natural question is, well, what are the rules? What are sort of the built-in safeguards of the system? So federally, every single state has to abide by the following 2 criteria. If you draw a district, the populations have to be balanced. So you can't have, at the congressional level, it's very close. You can only have a population deviation of 1 person. And then you also have to have Voting Rights Act compliance. So you cannot disenfranchise or block minority groups from being able to elect a candidate of their choice. So there's sort of some baked-in fairness principles in just the federal rules. There's also a host of common state and local rules. Okay, and so this idea of shapes being reasonable is a common one. And here we say compact, not the mathematical definition of compact, if you've been exposed to topology, but just we mean this, that the shapes kind of look pleasing to our eye. We also want to preserve boundaries. And two other local criteria that are sort of quite common is contiguity. So we are in Georgia. You don't want to have Atlanta and Athens connected. They are apart, right, geographically, I'm assuming. Okay, you don't want to have them in the same district, right? They have to be connected pieces. And then you have this idea of communities of interest, right? Groups with shared significant interests should be kept together in one district so they have a chance of electing a representative who will sort of pay attention to their policy needs. And so this last piece of communities of interest really ties back into that first idea, right? How do we ensure that marginalized populations are ensured fair representation? And so this is what we're going to focus on today. And so if we're thinking about fairness, right, we have all these legal criteria. How do we operationalize them? So I'm telling you things sort of in English about what is required for a districting plan, but we're not thinking about this mathematically yet. So there's this process of going from some sort of legal policy to a mathematical formulation of that problem. And this is one big theme in redistricting research, is how do you do this? So a team that I was involved in thought about this, but specifically for communities of interest in the most recent redistricting cycle. So I'm just going to remind you of the definition again, but the main thing is that for these local and state criteria, there are a plethora of states that require COI, community of interest, to be preserved when you're drawing the districting lines, okay? Except for what it means for those to be preserved is a bit hairy. It's not extremely explicit from state to state, but it is sort of a requirement for many, many, many states in the United States. And so some issues. If you are trying to identify a community of interest, you usually have a town hall, some sort of forum publicly where people are giving narrative or verbal testimony to describe that community, right? And so there's a gap between the words that people are saying and the text that's scribed somewhere and the actual geospatial process of drawing a districting plan, right? So there's a gap between testimony and line drawing. And there's also a lack of consensus on how to identify relevant communities of interest, okay, as well as how to measure the compliance of a community interest to a map. So this is precisely what we were trying to address. We wanted to take this sort of idea that communities should be preserved, and we wanted to make it very explicit mathematically in such a way that our community partners would be empowered to sort of push for communities of interest to be preserved and taken more seriously in the last redistricting cycle. And so the general approach that we're going to focus on is thinking about a community as a shape, okay? And then using mathematical tools to compare the shapes and see if we can kind of analyze communities of interest that way. This is the plan. So I want to pause here and ask, are there any questions about anything that I've just said related to redistricting or communities of interest? I have this done in parts, and so there's going to be breaks at each part to kind of make sure we're all on the same page. Because it's early and it's like too early to be lost, you know? Any questions? Okay, I believe that means no. Alrighty, so next, I want to sort of deviate and just talk about some mathematical background related to this issue. So I said I wanted to talk about shape comparison, right, to get back at this idea of thinking about how do we compare communities eventually. We're not there yet. So my question, and this is an actual question, is which two shapes are most alike? Circle and octagon? Okay, so circle and octagon are most alike. Why? So I heard ratio of perimeter to area, and then what were you saying? Okay, she's saying you can describe almost every shape as circles. So we've got two formulations of alike. Can we have like one more, I don't know, example, which, like someone from this over here, which two shapes are most alike to y'all? Okay, so you could kind of do some sort of intersection and see this way. So which two would you get then? Circle and octagon. Okay, so we have a consensus. So let's see. There is no answer, right? I just wanted to kind of brainstorm. But what you were doing, though, is you were sort of making mathematically precise the idea of what it means for two things to be similar. And you sort of either explicitly, we have an intersection, or ratio of area to perimeter, right? But you're quantifying this idea of similarity between these abstract shapes. Right, so let's say we put the shapes in the bag. So this is gonna be a bag for the whole talk. Maybe it looks like a vase, I don't know, but it is a bag, just as an FYI. And if we're thinking about how far apart they are, right, if we wanna be precise about quantifying their similarity, we can ascribe a distance between them. So we can represent that distance with those distances with the following matrix. So the first thing that we do is we put zeros along the diagonal to indicate that the distance from a shape to itself is 0. So the distance that was chosen, what is here? This was inspired, I think, from another group of students. Let's see. What we did was we looked at the vertices. So piece of K is a polygon of K vertices, and the distance was 1 over the absolute value of the difference of the vertices. I don't know. Maybe you pick a different distance. It's really not that important. The point is that we can develop a distance. We run into some issues here dividing by 0. I think we tried to avoid that by saying that we assume that it should be fine. This isn't the point. I'm going on a tangent with myself. The point is, we can ascribe a distance between these shapes just sort of arbitrarily. And so what I've done here is just sort of fill in this distance matrix based on this rule. And you'll notice that, as n is increasing, the distance between the circle and the polygons of n vertices is getting smaller, right? It's going to get really, really, really small as the number of sides continues to grow. Okay, so once we have a distance, what can we do? So one thing that we can do is sort of use the distance to create groups in a collection of shapes. So for instance, if we look at our distance matrix, we see that the circle and the heptagon, it is heptagon, right, for 7? Okay, I knew this was the right crowd to ask. So the circle and the heptagon sort of are at distance 1/7, right? So if we look at this diagram to the right, which is called a dendrogram, we have a scale which is giving parameters of distance. And so at parameter 1/7, the circle and the heptagon will be grouped together because that is their distance in the distance matrix. Similarly, the heptagon at 1/6 is going to be grouped with the circle, which is already grouped with the heptagon. And so the hexagon joins this group at 1/6. And we can sort of continue to read through the matrix and combine these groups of shapes until we get one giant cluster after parameter 1/4. And so this giant sort of red line through this dendrogram is a cut. And what this cut is doing is allowing me to just pick an arbitrary grouping. So this cut splits these shapes into 4 groups. This group with the triangle, this group with the square, the pentagon, and then these 3 form a group given this cut right here. And so what I want to sort of focus on is that once we have a collection of shapes, we can ascribe a distance between them, right? This allows us to be more precise about what it means for them to be similar. We can create diagrams like dendrograms, we can cluster, and we can also use metrics, these distances, as tools for classification. So for instance, if we have a database or collection of objects or shapes, and we already have them grouped into classes, then if we have a new object, right, and we want to know which class it belongs to, one simple way to do this is to assign that object to the class of the object to which it has minimal distance in the collection. Okay, and so I'm just trying to give a big picture overview of once you have shapes and you have a notion of distance between them, how this can sort of aid in different types of tasks. So for instance, with the new notion of distance, we could determine, where this star would belong in this group of shapes we started with. Okay, so this is just an overview of kind of like a big picture thoughts about shape comparison. I want to just very briefly motivate metric spaces and then go back to our target application of communities and redistricting. So I think calculus, somewhere between calculus and maybe analysis, we are introduced to convergent sequences of real numbers. So I feel confident that this is a concept that we've all been introduced to. And so the idea is that we have a sequence and it is converging to a limit. And how do we know this? We know that after a particular point, quantified by some natural number n, every point in our sequence is within epsilon of that limit, okay? And that's expressed by this absolute value here, right? The absolute value on the real line. And so the question is, we've been introduced to convergent sequences of real numbers. What about convergent sequences of other things, right? Like, it makes sense that there's a notion of convergence for things that aren't just numbers. And this is what metric spaces help us capture, but we need to shift from thinking about the absolute value as sort of a distance to something more arbitrary so that we could, perhaps quantify and have a sequence of shapes converging to something like a circle. So to me, this is sort of the motivation for why we want to think about metric spaces. So let me just introduce you to the definition before we go back to our target domain. So formally, a metric space is going to be a set X, right, that's non-empty, and a distance function. So this distance function is taking 2 points in your space, and it's spitting out a real number, right, that's positive based on condition 1. Okay, and what this is telling us is that real number is our distance that we've assigned between the 2 points in our space. So we kind of were arbitrarily making up metrics in the last couple of slides, and it becomes a distance function if it satisfies these 3 criteria. And the pair of the space and the distance together is what is known as a metric space. And so I want to give a couple of examples. The real numbers Rn are a metric space equipped with various distances. So one very common one is the Euclidean distance, the straight point between 2 lines in the plane. Another one is the taxicab distance, also known as the Manhattan distance. I guess also I call it the rideshare distance because taxis are less common these days. But what you're doing though is you're going up and down and right and left are the movements that you can make. So to get from this point to this point, we go 1, 2, 3, 4, 5, 6. But notice we could also go 1, 2, 3, 4, 5, 6. We could go 1, 2, 3, 4, 5, 6. It doesn't actually matter. And so typically you'll just see it expressed as the sum of the differences in the absolute values of these components. And the thing that I want to point out is that when we have, is that we can put 2 different distances or turn the same space, non-empty set, into a metric space with 2 different distance functions, right? And so we have the same points, we're on the same plane, R2, but we have 2 different distances, and so we get 2 different metric spaces. And we can actually compare them, which is really nice, because when you are a data scientist and you're kind of coming up with ad hoc dissimilarity measures, they're not usually comparable. So this is one advantage of working with metrics directly. The next examples are, I think, a bit more fun. So if we take our set to be the set of strings of length n, here I believe that there are n components, not n, excuse me, 9, but I don't want to count right now, but I think there's 9. They differ in 3 positions, right? And so the Hamming distance between A and B here would be 3. And so we have our set X, set of strings of length 9, and then we have our distance function, the Hamming distance. It turns that into a metric space. Similarly, if we have a graph, which is a collection of vertices and edges between them, we can take the vertex set of that graph, and we can take the shortest path between vertices to be a distance, and then that turns that graph into a metric space. More formally, write the set of vertices into a metric space. And so the last example of a metric space that I want to talk about is the set of compact subsets of a compact metric space equipped with the Hausdorff distance. And so I want to first build up the Hausdorff distance. So we've talked about sort of a set X and just a distance, but how do we know the distance between like a point and a set? So the Hausdorff distance is giving you a way to quantify how far apart 2 point sets are. It's used quite often in computer vision tasks, and we use it in the project that I'm going to talk about in just a few slides. And so if I want to know the distance between a point and a set, right? So what I'm going to do is I'm going to take my point X, and I'm going to think about all the points in Y, and I'm going to look at the distances from X to every single point in Y and find the smallest one if you're in a finite set. Okay, and that's what we can define as this d of xy here. And then if we do this for every point X in a larger set, we want to take the maximum of those minimum distances. And so if you've not seen this before, the main thing to focus on is just that this metric, this distance, when you symmetrize it, is going to allow us to turn the set of subsets of a metric space into a metric. So we have a metric space. It has subsets, right? And the Hausdorff distance allows us to quantify the distance between them. And it turns that into a metric space. And so this is going to be very important for our domain application because we're going to compare communities of interest using a modification of the Hausdorff distance. And so I'm just reiterating because I'm kind of going through this quite fast, and I will pause again for questions. But why do we care about metrics when we talk about shape comparison? They allow us to be precise about the distance between things. There are many ways to compare shapes, but this is precisely the one that I want to focus on today. The Hausdorff distance allows us to quantify the distance between two metric spaces, okay? And they're really useful in applications. And so once again, some of the things that we can use them for are similarity measures. For instance, between shapes, we can use distances and metrics to cluster and for classification tasks. And so I want to get back to the social problem and talk about how the tools from metric geometry are going to be used there. But I want to once again pause and ask if there's any questions from the audience on sort of what I just talked about in that section. Or any clarification questions? Yes? Can you repeat the question? Okay, so so the question was, how do you measure the precise, so I'm saying that you can be precise about the distance between things. So there are many metrics that are theoretically plausible and difficult to compute. This is a problem, and so you have heuristics that allow you to compute them or algorithms that allow you to approximate the true distance of a metric. In the examples that I'm going to talk about, we could actually compute the metric explicitly, but there are theoretical metrics that are hard to compute. So it just depends on the metric that you choose, how precise you're able to be in practice. So if you're someone like myself who's coming from a pure math background, you're happy that metrics exist and they have these nice theoretical guarantees, but not all of them are great for applications. Yes? This one? What's the Hausdorff distance between A and B? Okay, this is another geometric interpretation of the Hausdorff distance. So I was talking about building it up from like the distance from a point to a set. Another way to think about this is in terms of thickenings. So a thickening would be take a set and create sort of like a border around it of a particular width. And that band is going to be the thickening of that set. So maybe call it a delta thickening if I'm making it delta thicker. Okay, and so the Hausdorff distance can also be interpreted as if I take a set A and I thicken it until a set B can be contained in A, and then I thicken B until A can be contained in that, what's the smallest delta that I can choose as that thickening so that that proper relationship works? It wasn't the smoothest explanation, but this is what these pictures were trying to convey. The Hausdorff distance can also be thought of sort of geometrically as the minimum delta that you choose, so that with that delta, when you thicken A, you can fit B inside of that thickening, and when you thicken B, you can fit A inside of that thickening. Yeah? You want it to be completely contained. So like if they're touching here, but if I did like a small thickening, it's not completely containing B. So you want it to contain the entire subset. But if they're already touching, you're off to a good start. Yeah. Any other questions? Okay. So going back to the analysis of our Communities of Interest project, I just want to sort of recall the issue at hand, right? We're trying to contribute to fairness in redistricting by quantifying this notion that people with shared policy concerns should be kept together in communities of interest when people draw lines for new redistricting maps. However, there's a gap between the verbal articulation of where a community is and a geospatial representation of that community. So what we want to do is find a way to get a geospatial representation of a community and then summarize and collect data using tools from shape comparison like the metrics we just talked about in the previous slides. And so this effort, this project to quantify communities of interest was a large-scale one that involved 10 states in the last redistricting cycle, and I've listed the 4 states we work with the most: Michigan, Ohio, Wisconsin, and Missouri here. Nope. Okay. And then this was also led by the Metric Geometry and Gerrymandering group at Tufts, which is led by Moon Duchin. And then there was local support from people in Columbus, Ohio. For instance, at Ohio State, there was the Curran Institute for the Study of Race and Ethnicity, as well as the Ohio Organizing Collaborative organization. And so what we needed to do was to get community of interest data, right? We need to go from narrative-based testimony to some sort of geospatial product, and we needed to get the data. And so we did this through participatory mapping, this idea that the community is going to electively come and tell us where their communities are. And so they used a tool called Districtor to map their communities online. So each state had a public portal, and we trained trainers to equip the public to draw their communities. And then once those trainers knew how to draw a community or instruct the public, then they would go and they would train someone else, and then those people would go and they would train someone else. And this is sort of the model that we used to get people to use our tool in sort of a widespread way across these 10 states. And the community partners were supportive in that within our mapping tool, they helped us with local knowledge. For instance, in Ohio, we split the state into 6 zones based on the recommendation from people at the Kerwin Institute for people to use to map those communities. So this is what it looked like, the data. It was a shape, a polygon, this, right, layered on top of a map, and then narrative text data. So because I just finished this postdoc at Ohio State, I pulled from the portal someone describing the Ohio State community. And so the issue is that if you get 100 people to describe a campus, they're all going to describe it differently. And so someone else's shape might include things or regions a little bit further off the map here. And so the question is, how do you come up with an aggregate product that represents sort of Ohio State as a community, but takes into account all of the different ways that it was mapped in the software tool? So here are just other examples of the types of shapes. Some are less jagged than the one you saw before, but each piece of data was comprised of a shape, a polygon representing a community, and narrative text data of people describing what are the issues in that community, what do we care about. And so what was our task? We have thousands of polygons and text submissions in each state, right? And we want to aggregate them into some sort of product. And so for each submission or collection of submissions, we wanted to group them. We wanted to group them into clusters and then create sort of summary polygons that described, you know, in totality, to the best of our ability, all of the submissions that were in a particular cluster. And so clustering is our aggregation tool. There are other methods. This is just the one that we chose. But this is our task at hand. We got the data, then we had to find a way to synthesize it. And so now we have another bag. Remember, this is a bag of shapes, but now we have communities, these polygons that are user-drawn that we need to find a way to aggregate. So we need a distance between them. And so the users are seeing our polygons as sort of these mapped out regions in their Districtor tool, but what they really are to us are graphs. Okay, so given a state, we can create what's called a tiling by thinking about pieces of geography called census blocks. And so census blocks can sort of light up a state. So every person is sort of grouped into a particular census block, and they have the same population. And so we can take all the census blocks in a state and make them nodes. And because those represent geographic regions, we can connect the nodes if they're geographically adjacent. And this is going to give us a tiling of a state. It's going to give us a graph. Okay, and so when people are going into our software tool and lighting up a community, what they're really doing is they're drawing or indicating particular census blocks on this dual graph. Okay, and so when we think about communities of interest from our data science team, we're really looking at subgraphs of this larger graph of the state. And so now we have 2 point sets that are sort of representing communities, and this is what allowed us to use the Hausdorff distance as an aggregation tool. Okay, and so if you recall the Hausdorff distance, the distance between a point and a set, you look at the distance between that point and all other points in the second set, and you want to take the minimum. Instead of taking the maximum of those minimums like you do for the Hausdorff distance, we took an average to protect against outliers. And this allowed us to create a distance between communities of interest. And so once we had that distance, we could create a distance matrix, right, a dissimilarity matrix, and then this allows us to do things like cluster, like what we did in our sort of toy example with just the shapes and polygons. And so I can be more precise here. What we were doing a couple slides ago with the shapes, the circle and the squares and the heptagons was called hierarchical clustering. And so this is a clustering that happens when you take each single point in your space as a cluster initially, and then you start to group them together strategically based on some sort of distance rule. The rule that we used was called complete linkage, and that's not so important. I'm happy to talk more about linkage-based clustering if anyone has questions after the talk. But the point is that for us, each submission from a community member started off as its own cluster, and then we started to group them together based on this modified Hausdorff distance. We ended up with a dendrogram, and we were able to make a cut of the dendrogram based on the recommendations of our community partner. So if our community partner said that they wanted more submissions in a particular cluster, then we could change our choice of cut appropriately. Okay, and so the outcome of this process is a collection of geoclusters. So we have a collection of submissions of different shapes, and now we have sort of big groups of clusters representing communities in a particular region. And so here's an example of what that might look like for Michigan. Okay, so we have 59 submissions that all got sort of heat mapped onto this geographic region as a community cluster. And so this is what a COI would look like. However, there were cases where the community partner didn't want to have a cluster with a certain number of submissions, and they wanted us to make it smaller. Okay, and so to deal with large geoclusters, we use the narrative data, because up to this point, we're only using the geospatial information. So we use the narrative data to create subclusters. Okay, and so the narrative data, once again, are people just describing what's important to them. So 100 people could draw the same geographic area, but people could have very different interests. And so you could end up having sort of disjoint narrative themes, but cohesive geography. And this happened several times. And so the way that we chose to compare the narrative submissions, initially we tried to do some natural language processing. That did not work. And so we elected to just associate to each narrative text a vector that sort of highlighted the key themes that we had noted amongst all of the submissions with just a binary vector of zeros and ones. And so in this submission, for instance, we see that job opportunities is highlighted, and so we would have a 1 for economy. And so what this allowed us to do was to each submission associate a vector, and now when we're comparing submissions, we're really just comparing these vectors. So now we have a bag of different shapes, where these shapes are just binary vectors representing the text data. And the way that we ended up comparing this was using something like a Hamming distance, Jacquard similarity. And so we talked about a Hamming distance a few slides ago, and this is precisely what this numerator is doing. It's an intersection score of how many themes that each community of interest had in common from a semantic point of view, divided by its union score. And so we took these, and that allowed us to sort of subcluster these larger geographic regions. And once again, I can kind of talk about the weeds of how that really worked. It involved Markov chains, but this is sort of how we incorporated the text data in our project. And so, for instance, you could have overlapping geographic regions that are sort of very similar, but narratively distinct. And so what was the outcome? For instance, in Ohio, we ended up with 22 community clusters. In Michigan, we ended up with 34. This highlights sort of the majority of the communities were in this zone for Michigan. And then for our subclustering, right, we had issues like this where we would have something like the Lansing area that we would then turn into two narratively distinct subclusters, even though they were in the same geographic space. Okay, and so this was joint work with Aaron Chambers, Moon Duchin, Parker Edwards, and Ari Stern, and what it really represented was the first systemic effort to collect and aggregate communities of interest through participatory mapping. So once again, there are all of these sort of fuzzy rules in redistricting that sound fair, but how do you actually implement them in practice? And our goal was to try to develop an aggregation pipeline that would input community submissions and sort of output some sort of common product of communities in that state. So now, when we want to see if communities are preserved, we have a geospatial representation for them. And we did also develop a score for compliance. I just have not talked about it today. And so going back to this framework, right, the whole goal of quantitative justice is we're trying to address something from like a social domain. And so the output, once again, isn't just research papers or talks. We're really interested in contributing to some community partner. We're interested in contributing to equity in some form. In the case of this community mapping project, this is a report from the Ohio Citizens Redistricting Commission. And so I was able to attend a hearing, and they handed out these reports. And this is the page where I flipped to the community mapping project, which was really exciting to see them talk about this in real time, about the effort that they had done to try to make this more explicit. That's me at the hearing. And so I talked a bit about fairness and redistricting from this perspective, and I want to just pause because I see that it's 9:25, but that doesn't mean anything to me because I don't know what time the talk is over. 10 minutes? Okay, great. So I talked about quantifying fairness and redistricting from this perspective of making communities more explicit mathematically, right? But I want to just sort of talk about a general theme in redistricting, which is how do you know if a map is fair? This is a very common question, and I want to just briefly mention an approach called ensemble analysis that's used for outlier detection. And the idea is the following. If I want to know if something is fair, I need something to compare it to. Fair compared to what, right? And so one technique that mathematicians have been using is to generate thousands of alternative plans. So I have a map. It may be kind of stinky, like I think it's not good, right? But I don't know how to say so explicitly because I need to show, I need to somehow to quantify how bad it is. So I create a collection of plans. And so the analysis usually looks like the following. Let's say I have a particular plan. So in this case, in North Carolina in 2012 and 2016, their congressional maps were challenged. And I look at that plan, and I want to know how many Democrats were elected given an election, right? And then I want to ask that same exact question for each of these plans in my ensemble. In the graph that I'm showing you, there were 30,000. Okay, that's going to give me a distribution of how many Democrats are elected in this particular, for a particular election. And so what you can see is that for 30,000 plans, the two maps that were being challenged were sort of extreme outliers in that distribution. And so this technique is one that's been used very successfully in court litigation to sort of challenge existing maps. And so one thing that really draws me to this work is that it actually is sort of out there on the front lines in a lot of voting rights litigation. And so over the summer, I don't know if you were following the Supreme Court rulings, there were a lot of them that came out. The affirmative action one was a doozy. I digress. And so this one, I wanted to share what is going on in the conversation in the opinion of the court. They're talking about the universe of possible districting plans. This is a technique that's been popularized by mathematicians over the last decade. They're talking about how it's impossible to enumerate all the plans, about how it's not easy to identify an average map, right? They're sort of having a meta conversation about the challenges of generating these collections of plans and not understanding them very well. And so this is sort of something that motivates a lot of the research that I'm interested in doing in the future in this field, which is how do we understand this space of valid districting plans? So in particular, right, if I'm thinking about maps now in my bag of shapes, how do we quantify distance between them? How do we compare two plans? Because if we can, right, we can develop clustering techniques that allow us to identify themes of redistricting plans. We can do classification. We can do a whole lot of things. We can identify an average map, a median type of map with the metric. And so this is something I'm very interested in and I'm working on presently. I'm doing this at the Simons Law Firm Mathematical Sciences Institute as part of their semester program on algorithms, fairness, and equity, and I appreciate their support. And I'm getting better at acknowledging people, because my mentor was like, you don't have an acknowledgement slide. I was like, oh, whoops. And so I also want to acknowledge the National Science Foundation. The current postdoctoral award that I have has changed the trajectory of my career. And I just wanted to finish with a plug for quantitative justice. Research in this area is not common. When I was learning and sort of growing into mathematics, I loved it, but it had absolutely nothing to do with the things that I cared about in my personal life. And I was fine with that, kind of, right? I sort of did a lot of outreach and other things to scratch that itch. And I just wanted to note that this research field sort of allows for the bridging of the gap between scholarship and activism. It allows for us to sort of bring in relevant examples into our classrooms and our research and our teaching. And the thing that I wanted to note is that the AWM, and what's really exciting me about this organization is that we're here to sort of promote equity amongst women and gender minorities in math. And so if you don't take anything else from my talk today, just remember that you deserve an equitable society, and you deserve an equitable mathematical community, and you deserve to be here, and you are wonderful. So if you have any questions about anything that I've described today, I'd be happy to talk to you after the talk or anytime, just come and find me.
We do have time for just a few questions.
Yes.
When labeling the data,
Mm-hmm.
was there any consideration about like whether a word can have both a positive or a negative connotation?
Yeah, yes. So the thing about this process is that we did it over sort of, we had like a finite amount of time, which was really different for me because in sort of redistricting, they need things like yesterday, whereas mathematically, you usually have time to kind of sit with an idea. So the thing that we were able to do was we identified all of those themes via topic modeling and sort of just hand sort of like picking out themes for actually reading submissions. And then there was a team that just went into a room for a weekend and just read them all and sort of highlighted it. So any nuances in positive or negative with respect to the terms would have had to have been picked up by the particular human that read that submission. So it was subject to error, but perhaps less so in terms of like the what is it called? Not semantics, but in terms of like the feelings of positive or negative, because a human is going to pick up on that more than like, you know, if you put it through some sort of algorithm. Does that answer your question? Yeah. Yes. It just means that, well, from a geographic perspective, it just means that the block groups that comprise that, like the geographic cluster, they overlap, right? So it's going to pick up, so the distance that we use for clustering is going to be small when there's just a substantial overlap of those communities. And so,
I'm a mathematician, I want to know what substantial means.
I would have to look in the weeds of the appendix to get the numbers. Yeah, but I can certainly do that once I get off the stage. Yes?
So you showed the example of Lansing, Michigan, and from my understanding, it was overlapping, but you wanted to split it into two groups. And so you did that for the same geographic area, but based on like different interests.
Yeah.
How does that go to a report affecting the congressional boundaries?
Yeah, so all of these went into a general report. That one for Lansing went into a report for Michigan, and Michigan's commission was actually empowered to draw the lines, unlike the ones in other states. So it's just something that would need to be noted, right? Because in the line drawing process, you're really just worried about, did you cut it? And so in that case, if you have two distinct communities semantically, even though they're geographically similar, then you're just going to try to, preserving the larger one is going to necessarily sort of preserve the two smaller ones. Yeah, so that nuance wouldn't be picked up in the line drawing process as much, but it would be sort of reported and identified that these are two distinct communities which wouldn't have existed before these sorts of efforts. Yes?
So when the tool itself that you're training people to then train others, is like when you're selecting an area, does it just grab the whole census block?
Yeah, it does. So it wasn't freehand, it was pre-populated with those census blocks. Yeah, otherwise we would have had like fractions of, and it would have been very hairy.
Any other questions? Then let's thank our speaker.
All right, I will turn the mic over to our president, Dr. Washington, as we transition.
Hi, good morning, everyone. Fantastic talk. Thank you so much. Very inspiring. And so, good morning. Hope y'all having a good time. And we're going to now go into our Sunday morning sessions down the promenade. We call it the promenade. Don't ask me to spell it. It's a walking pedestrian pathway. And then at 11:35, we'll be in for a treat from NSF. And we all know what happened last night, right? The government did not shut down. What a relief. Well, 45 more days is greater than 0, so we'll take it, right? Okay, so we'll have an NSF panel. So look for the wonderful, I think, informative discussion, and come with questions.